A stone exists that modern tools cannot reproduce. It whispers of a forgotten chapter in our story. This video explores 25 mysterious artifacts from the medieval world and earlier, each one bearing the subtle, impossible marks of advanced ancient machining. By the end, you will see a hidden pattern in history that challenges the very timeline of human innovation. How did a complex bronze computer exist 2,000 years ago? And why do Egyptian granite boxes display a precision that defies simple tools? What does it truly mean to look at the past with fresh eyes? That blacksmith's hammer striking glowing iron is the iconic sound of medieval craft. It represents immense skill, patience, and human force shaping the material world. But what if we told you some objects from the distant past bear marks that this hammer could never have made? They whisper of a different sound entirely, the steady, controlled hum of a machine. To understand this mystery, we must first define our terms. What do we mean by advanced ancient machining? It is not merely about skilled handiwork, which the ancient world possessed in abundance. It is about a specific, measurable quality of manufacture that aligns with principles we associate with the machine age. Engineers and researchers like Christopher Dunn approach these artifacts not as archaeologists, but as machinists. They ask the questions a factory foreman would ask. How was this surface finished? What tool path created this groove? What tolerance was the maker aiming for? The answers often point to capabilities that seem out of place. We are talking about geometric perfection. Think of surface flatness so precise it can be measured in wavelengths of light, a concept meaningless to a stonemason with a copper chisel. Consider internal corners that are perfectly square, not approximately, but mathematically 90 degrees, a feat incredibly difficult without a milling machine. Symmetry that is not just visually pleasing but mechanically precise, indicating rotation on a fixed axis like a lathe. These are the benchmarks. This is the foundation of our exploration. We are not looking for magic. We are looking for the fingerprints of a technology that has been misplaced in our historical narrative. With this understanding in place, the true strangeness of the artifacts we are about to examine will come into sharp, unsettling focus. That hum of a machine we just described has a real-world echo, and it comes from the bottom of the sea. In the year 1900, sponge divers working in the deep waters off the coast of the Greek island of Antikythera made a startling discovery. Among the broken statues and ceramics of a sunken Roman cargo ship, they pulled up a lump of heavily corroded bronze, overgrown with centuries of marine life. To the untrained eye, it was just scrap, but this unassuming object, now known as the Antikythera mechanism, is perhaps the single most disruptive artifact ever found for our understanding of ancient technology. Dated to around 100 years before the Common Era, it was not a statue or a weapon. It was a machine, a complex hand-powered bronze analog computer. For decades after its recovery, its true nature remained a mystery hidden under its calcified crust. It was only through painstaking research, using advanced imaging techniques like X-ray tomography, that its secrets were slowly revealed. Inside that lump were the remains of at least 30 interlocking bronze gears, neatly housed in a wooden frame. This was not a simple clock. This was a device engineered to model the cosmos. By turning a hand crank on the side, an operator could calculate the positions of the sun and the moon, predict lunar and solar eclipses, and even track the cycles of ancient athletic games like the Olympics. It displayed this information on dials on both its front and back, a miniature planetarium powered not by electricity but by genius. The true shock for researchers like Michael Wright, who dedicated years to building a working reconstruction, lies in the manufacturing of those tiny gears. Some of them have teeth cut at precisely 60 degrees, a feature that would allow them to mesh smoothly and transfer motion with minimal error. Creating such a gear by hand with simple files and chisels is not just difficult, it is borderline miraculous. The consistency required suggests the use of a form of basic machinery, perhaps a dividing plate or an indexing mechanism. This is a tool to make tools. It hints at a workshop where the principles of mass production and precision calibration were understood, at least for specialized devices. This one object, pulled from a 2,000-year-old shipwreck, shatters the comfortable idea of linear progress. It places a device of breathtaking mechanical sophistication in an era we still often picture with simple levers and pulleys. The Antikythera mechanism does not just tell time, it asks us a profound question. If this survived the sea, what else was lost to history? The mechanism's intricate gears speak of a mind that understood the heavens as a clockwork system. Yet to find evidence of that same mechanical precision carved into immovable stone, we must journey from a Greek shipwreck to the dry sands of Egypt. Deep beneath the sands of Saqqara, an ancient necropolis dedicated to the sacred Apis bulls, lies a corridor of silent giants. This is the Serapeum. Here, in shadowy, man-made caverns, rest colossal boxes carved from a single, solid block of granite and rose quartzite, some weighing over 80 tons. Attributed to the late period of ancient Egypt, their official purpose was as sarcophagi, final resting places for revered animals. But to stand before one is to feel a different kind of reverence, one tinged with profound technical confusion. The exterior surfaces of these boxes are not merely smooth, they are flawlessly flat across areas wider than a person is tall. Their corners are not roughly hewn approximations, but geometrically perfect 90-degree angles inside and out. This is where the quiet argument for lost methods begins. Granite is one of the hardest stones on Earth. The conventional toolkit for the era consisted of copper chisels, stone dolerite pounders, and abrasive sand. With these tools, skilled artisans could certainly shape granite given enough time and effort. They could create beautiful statues and imposing obelisks. But the result of pounding and grinding is a wavy, undulating surface, a testament to human force. What we see in the Serapeum boxes is different. The consistency of the flatness suggests something else entirely, a large, stable cutting tool that moved in a perfectly straight line, removing material with even, controlled passes. It is the difference between sculpting by hand and planing a board with a machine. Then there are the internal corners. Inside these massive lids and boxes, where the stone was hollowed out, the corners are sharp, clean, and square. Try to visualize carving out the inside of a granite block using a hammer and a copper tube with sand. You might create a rounded interior, but achieving a perfectly square internal corner, deep inside the stone, is a monumental challenge. It implies a technique that could remove material efficiently from a confined space, something akin to a modern milling or drilling process. These boxes do not shout their mystery, they embody it in their sheer, silent perfection. They sit as a monumental question mark in stone, asking us how, and perhaps more intriguingly, why such impossible precision was devoted to creating them. That silent perfection in stone is one kind of mystery, but what about a whisper of power? From the colossal stillness of the Serapeum, we move to a small, unassuming clay jar that could hold an entirely different secret. Found in the 1930s near Baghdad, this simple vessel, roughly the size of a man's fist, dates to the Parthian or Sassanid period, a time between 200 years before and 200 years after the Common Era. It looks utterly ordinary until you see what was sealed inside. The jar contained a rolled copper cylinder, and within that, an iron rod. The whole assembly was capped with an asphalt plug, creating an insulated, self-contained unit. This is the artifact often called the Baghdad Battery. Its proposed function is one of history's great debates. When filled with an acidic electrolyte like vinegar or wine, the jar creates a measurable, though very small, electrical potential. Could it have been an ancient galvanic cell? The possibility is tantalizing, suggesting a fleeting grasp of electrochemical principles centuries before such science was formally understood. But for our search, the true intrigue is not just in what it might have powered, but in how it was made. Look at the copper cylinder itself. Its walls are remarkably uniform in thickness. Its diameter is consistent along its entire length. This is not the work of a metalsmith simply hammering a sheet of copper into a rough tube. Hammering by hand inevitably creates variations, slight thick and thin spots, a waviness in the metal. The consistency seen in this cylinder speaks of a different process. It suggests the use of a form of basic machinery to achieve standardization. One possibility is a simple lathe, where the copper could have been spun and shaped with a fixed tool to ensure perfect symmetry. Another is a draw plate, a tool with graduated holes that would pull the metal through to form a tube of exact dimensions. This is a subtle but profound distinction. It moves the object from the realm of skilled craft into the realm of precise, repeatable manufacture. If this jar was indeed a purposeful cell, then it represents a fusion of two advanced ideas. First, a conceptual understanding of chemistry and electricity. Second, the mechanical capability to produce the standardized parts necessary to exploit that knowledge reliably. It hints at a workshop where experiments were not one-off curiosities, but could be replicated, where the components were not unique artworks, but interchangeable pieces of a larger, unknown puzzle. The Baghdad battery, whether a cell, a storage vessel, or something else entirely, stands as a quiet testament to a level of technical thinking we are only beginning to appreciate. It asks us to look past its humble clay exterior and see the precise, machined intent hidden within. That small clay jar hints at a potential for power, but to witness the raw, physical evidence of applied force, we must return to the stone. Scattered within the ruins of ancient Egyptian temples and quarries are curious objects that seem almost like industrial waste. They are drilled stone cores, cylindrical pieces of granite or diorite that were literally hollowed out from a larger block. One of the most famous sets comes from the Temple of Hathor at Dendera. To hold one of these cores is to hold a fossilized moment of machining in your hand. The outside of the cylinder is smooth, but it is the internal surface that tells the impossible story. Spiraling down the length of the core from one end to the other is a single, continuous groove. This is the mark left by the drill bit as it chewed its way through the incredibly hard stone, and it is this groove that engineers find so baffling. The groove has a consistent depth and a uniform pitch, meaning the distance between each spiral turn is remarkably even. This is not the erratic, wavering scratch you would get from a human worker laboriously turning a copper tube back and forth with a bow drill, using sand as an abrasive. That method creates a rough, uneven pattern, as human strength and rhythm inevitably vary. The groove on the Dendera core is different. Its consistency implies something far more steady and powerful. It suggests a drill that applied not just rotational force, but also a tremendous, constant downward pressure, sinking into the granite at a predictable, unvarying rate. This is what machinists call the feed rate. Imagine trying to push a drill into a solid block of granite by hand. Your arm would tire, the pressure would fluctuate, and the groove would show those variations. The core from Dendera shows no such struggle. The feed rate is smooth and mechanical. This points to a technology that could manage both immense weight and perfect control. Engineers like Christopher Dunn have proposed that such a feat would require a mechanical advantage beyond human muscle. Perhaps it was a weighted apparatus, a heavy drill head that provided its own consistent downward force as it turned. Or maybe it involved a more sophisticated feed mechanism, akin to the lead screw on a modern drill press, that mechanically advanced the bit into the work. This transforms the object from a simple artifact into a data point. That spiral groove is a recorded log of an ancient machining operation. It tells us that whoever made this understood rotational force, tool pressure, and material removal on a level that feels disconnected from the simple tools we picture in their hands. These silent stone cylinders are not ornate treasures, but they are perhaps more valuable. They are the undeniable physical proof of a process we have yet to fully comprehend. The spiral groove on a stone core is a physical record of force, but what about an object that seems to defy the very idea of force being applied at all? From the hard evidence of Egyptian granite, we move to a far more elusive and controversial mystery, one carved not from stone but from light itself. The crystal skulls, particularly the famed Mitchell-Hedges skull, exist in a hazy space between legend, archaeology, and outright deception, often linked romantically to ancient Mesoamerican cultures like the Maya or Aztec. Their true origins are shrouded in modern mystery. The most striking examples are carved from a single, flawless block of clear or milky quartz, a material harder than steel. Their alleged antiquity is not their only puzzle, it is their alleged perfection. Proponents of a lost origin point to two astonishing features. First is the absence of visible tool marks. On a piece of quartz carved with primitive tools, even the most skilled artisan would leave microscopic scratches and chipping, signs of the immense struggle against the material. Some of these skulls, however, display surfaces that are eerily smooth, as if the crystal simply grew into that shape. The second, more compelling feature is their anatomical precision. The cheekbones, the orbital sockets, the subtle contours of the forehead, all mirror the complexity of a human skull with an accuracy that feels studied, not approximated. The Mitchell-Hedges skull adds another layer of impossibility, a separate, detachable jawbone that fits perfectly with the cranium, a feat of joinery that would be challenging even with modern precision tools. This is where the machining argument enters the fray. Critics and material scientists note that working quartz to this level of finish, especially inside the delicate eye sockets and nasal cavity, would not just be difficult with hand tools, it would be nearly impossible without creating fractures. They suggest the kind of precision observed would require rotary tools like a lapidary wheel and abrasives harder than quartz itself, such as diamond dust. This is technology firmly placed in the modern industrial era, not in pre-Columbian workshops. The overwhelming consensus now is that the most famous crystal skulls, including the Mitchell-Hedges, are exquisite 19th or early 20th century fabrications, products of a burgeoning European fascination with the exotic. Yet, even as we dismiss these specific objects as modern hoaxes, they perform an invaluable service. They force a crucial act of separation in our search. They make us ask the hard question, what is a genuine archaeological puzzle, and what is a beautiful distraction? The idea of the crystal skull, the very notion that ancient artisans could have achieved such a thing, continues to fuel the discussion of lost lapidary techniques. It challenges us to look beyond the forgery to the deeper question: could a forgotten method, perhaps using patient, specialized abrasives and ingenious mechanical guides, have produced something remotely similar? The skulls, in their controversial glow, teach us that the search for advanced ancient machining requires not just wonder, but rigorous discernment. We must be willing to let go of the seductive myth in order to clear the path to a truth that may be even more surprising. Forging a blade in the medieval world was a gamble against impurities. A blacksmith would heat and fold iron, praying the fire burned hot enough to drive out the slag, the stony imperfections that made a sword brittle. The result was often a serviceable weapon, but one with a hidden weakness, a potential fracture line waiting for the stress of battle. Then there are the Ulfberht swords. Found across Europe, dating from the 9th to the 11th centuries, these weapons were different. Their blades bore a simple inlaid inscription, +sign ULFBERHT +. That name was not just a maker's mark, it was a promise of superiority. When modern metallurgists analyzed these swords, they discovered why. The steel was astonishingly pure. It possessed a high, uniform carbon content and was virtually free of the slag inclusions that plagued other blades of the era. This was not the layered, folded steel of a typical Viking forge. This was crucible steel, a material of such consistent quality it would not be matched in Europe until the Industrial Revolution, nearly 800 years later. The mystery here is not in the shape of the blade, but in its very substance. Achieving this purity is a feat of controlled environment, a form of advanced machining at the atomic level. To make crucible steel, raw iron and carbon sources must be sealed in a clay crucible and heated in a furnace to an extremely high, sustained temperature, around 1290 degrees Celsius. At this heat, the materials melt completely. The slag, being lighter, rises to the top, and the dense, homogeneous steel settles below. It is a process that demands not just intense heat, but precise control over that heat for many hours. The furnace must be designed to achieve and maintain a temperature that would have been thought impossible for a medieval bloomery. This suggests a profound and lost understanding of pyrotechnology. Furthermore, the consistency across dozens of surviving Ulfberht swords is telling. They were not one-off masterpieces born from a lucky batch of ore. They are products of a standardized, repeatable manufacturing process. Someone or some group possessed a formula and a method they guarded fiercely. In an age where a sword could mean the difference between life and a final rest, this secret was a source of immense power. The Ulfberht was lighter, stronger, and more flexible than its contemporaries. It could bend without breaking and hold a sharper edge, turning a warrior's strike into something far more decisive. This artifact moves our search from stone and gear to the realm of material science. It whispers of a workshop where fire was not just a tool, but a precision instrument where the goal was not just to shape metal, but to fundamentally transform its inner nature. The secret of the Ulfberht furnace died with its makers, leaving behind blades of impossible purity as the only evidence of a flame that burned brighter and smarter than history remembers. The secret of the Ulfberht furnace was a mastery of material from within. But what about mastering form from without on a scale that defies simple explanation? Deep in the humid jungles of Costa Rica's Diquis Delta, a different kind of artifact lies half buried in the earth. They are the stone spheres, hundreds of them, carved by a pre-Columbian culture that flourished over 1,000 years ago. To call them remarkable is an understatement. They are quite simply nearly perfect spheres. Some are small enough to hold in your hands, while others are monumental, over 2 meters in diameter and weighing several tons. They are carved from a tough, granitic stone called gabbro, and it is their geometric perfection that stops engineers in their tracks. Creating a sphere by hand is one of the most difficult challenges in stoneworking. It is not like carving a statue where you can work on one feature at a time. A sphere demands constant, holistic attention. Every strike of the tool must consider the entire form. To achieve the sphericity seen in the best of these objects, the artisans needed a way to constantly check their work, to measure the curvature from every angle and correct any high spots. How did they do it? With simple stone hammers. The process seems almost unimaginably tedious and prone to error. The most plausible explanations sound suspiciously like the principles of machining. One theory involves a form of large-scale lathe. Imagine the stone block suspended between 2 fixed points, able to rotate. As it turns, a fixed abrasive or cutting tool could be applied to its surface, slowly shaving it down into a symmetrical form. Another method might have used a precise template, a large curved guide that could be run over the stone to identify and mark areas that needed to be ground down further. This is not random sculpting, it is a systematic removal of material guided by a geometric ideal. Even more telling is the consistency found among groups of spheres. Researchers have noted that in certain archaeological sites, spheres were placed in alignments or groupings with others of very similar size. This suggests the makers were not just creating individual artworks, they were producing to a specification. They had a target diameter in mind and possessed the measuring techniques and production control to hit that target again and again. This moves the spheres from the realm of mysterious art into the realm of standardized manufacture. It implies a conceptual leap, a workshop understanding of volume, diameter, and sphericity that could be translated into a repeatable process. These silent orbs of stone are not tools in the conventional sense, but they are monuments to a technical mindset. They represent the moment when an ancient culture decided that a perfect geometric shape was so important that they would dedicate immense resources to inventing a method to create it, not once but hundreds of times. They are a physical argument for a lost school of precision engineering, one that thought in curves, consistency, and controlled, patient removal. The pursuit of perfect form in stone gives way to an object that plays with light itself. In the quiet halls of the British Museum rests a small, astonishing artifact from the late Roman world, a vessel known as the Lycurgus cup. Crafted in the 4th century, it is not merely made of glass, it is an engineered illusion. Hold it in one light and it glows a deep, translucent red. Shift it slightly and the entire cup transforms into a vibrant, glowing green. This magical property is not magic at all, but a staggering feat of ancient material science called dichroism. Modern analysis reveals the secret. The glass is impregnated with billions of microscopic particles of gold and silver, each one smaller than a grain of sand, measuring about 50 nanometers across. To achieve this, Roman artisans had to precisely control the composition of their glass melt and the conditions under which it was cooled, effectively creating a colloidal suspension of precious metals at a scale invisible to the naked eye. This is not accidental alchemy, it is a repeatable recipe for nanotechnology, a level of control over matter that seems impossibly ahead of its time. But the cup's mystery does not end with its chemistry. The glass itself was formed into a thick, solid block, and from this block the intricate scene that covers it was carved. This technique is known as diatretum or cage cup work. The outer layer of glass was meticulously cut away to leave a delicate, freestanding network of figures and vines that depicts the myth of King Lycurgus entangled by the god Dionysus. This is not molded or added on. It is all one single piece of glass, with the inner cup and the outer cage connected only by tiny, strategic struts. The risk of catastrophic failure here was immense. Glass is brittle and unforgiving. One wrong tap, one slip of a chisel, and the entire piece would shatter into worthless fragments. To execute such delicate, open-work filigree from solid glass implies tools of extraordinary stability and precision. Art historians suggest the use of small, rotary drills, perhaps with interchangeable bits made of hardened stone or diamond, mounted on a stable lathe-like apparatus. The artisan would have needed to apply perfectly consistent pressure, removing minute slivers of glass with the steady rhythm of a machine to prevent cracks from propagating. The Lycurgus cup, therefore, stands as a dual marvel. It represents a profound, scientific understanding of how to manipulate light at the particle level, fused with a mechanical mastery of cutting and shaping a fragile medium with surgical control. It is a silent symphony of fire, chemistry, and precision engineering, a reminder that the ancient world's brilliance sometimes shone in the most delicate and most luminous of forms. The delicate dance of light within the Lycurgus cup reveals a world of hidden control, but for a different kind of ancient mastery, we must look to an object that has stood, unyielding, against an entirely different force, the relentless passage of time itself. In the courtyard of the Quad complex in Delhi, India, a single iron pillar rises over 7 meters towards the sky. It is not ornate, not covered in intricate carvings. Its power lies in its silent, stubborn defiance. For over 1,600 years, through monsoons, scorching heat, and urban pollution, this pillar of pure wrought iron has refused to rust. While modern science attributes its remarkable corrosion resistance to a protective film formed by its unique high phosphorus content, this only solves half the puzzle. The greater mystery is how it was made in the first place. In the 4th or 5th century, the idea of casting such a massive iron object was impossible. This meant the entire pillar, weighing over 6 tons, had to be forged by hand. Think about that for a moment. Blacksmiths would have had to heat and weld together countless small pieces of iron bloom, one at a time, in a forge that must have been colossal. Each piece, glowing red-hot, would be placed atop the last and hammered until the metals fused into a single, continuous mass. This was not just a large project, it was an act of sustained, industrial-scale coordination. The consistency of the metal is what truly astounds engineers. There are no major slag inclusions, no weak seams where the welds failed. This indicates a process of unbelievable control. The temperature of the forge had to be monitored and maintained with precision across days, perhaps weeks, of continuous work. The hammering force had to be applied evenly across the growing pillar's surface, likely by teams of workers operating in a rhythmic, mechanical cadence. This transforms the act of blacksmithing into something closer to a production line. It was a form of machining through fire and force. The pillar is a testament to a forgotten industrial logic, where human skill was organized and amplified to achieve a result that feels monolithic in every sense. It stands not just as a monument to a king, but as a permanent record of a workshop that could think big and execute even bigger, with a level of quality control that has literally stood the test of centuries. The iron pillar in Delhi stands as a testament to scale and control, but for sheer, bewildering precision carved into unforgiving stone. Few places on Earth compare to the windswept plateau of Pumapunku in Bolivia. Part of the larger Tiwanaku complex, this site is not a palace or a temple in the traditional sense. It is better described as a sprawling, ancient factory floor, now frozen in time and shattered by some immense, forgotten cataclysm. Scattered across the ground are enormous stone blocks, some weighing over 100 tons, carved from andesite and granite, two of the hardest stones available. What makes these blocks so utterly arresting is not their size but their geometry. They are not simple rectangles, they are complex, interlocking puzzles. Many are fashioned into perfect H shapes, with precise recesses and protrusions that look like giant stone Lego bricks. But it is the fine details on these megaliths that whisper of a technology out of place. Look closely at the surfaces. They are not just flat, they are often flawlessly smooth, with a consistent finish that looks less like chiseling and more like milling. The edges are sharp, the corners are crisp 90-degree angles, and across these faces run shallow channels and notches with parallel walls and uniform depth. Some blocks feature rows of small, drilled holes, each one identical in diameter and spaced with mathematical regularity. This is not the work of artisans approximating a design. This is the work of engineers following a blueprint. The precision of the interlocking joints is particularly telling. For these massive stones to fit together without mortar, the tolerances had to be incredibly tight, perhaps within a single millimeter over several meters. Achieving this by eye with simple stone tools borders on the impossible. It strongly suggests the use of physical templates and measuring guides. A master template, perhaps made of wood or a softer stone, could have been used to trace the complex profiles onto each block, ensuring every H was identical. More striking is the implication of the tooling itself. The consistent depth and width of those channels and notches points to a cutting implement that could make repeated, identical passes. Imagine trying to carve a perfectly straight, half-inch deep groove 10 feet long into granite using a hammer and chisel. Your depth would waver, your walls would wobble. The grooves at Pumapunku do not waver. They suggest a tool mounted in a fixed guide, perhaps on a track, allowing it to move in a perfectly straight line while maintaining constant pressure, sinking into the stone at a predetermined mechanical rate. This is the language of mass production. Pumapunku feels less like a construction site and more like a pre-industrial assembly yard, where standardized components were manufactured with such exactness that any block could fit with its counterpart. The ruins present a silent, stone-cold argument for a system, a forgotten school of construction that valued precision, repeatability, and interchangeability over 1,000 years ago, principles that would not become commonplace until the modern factory age. Pumapunku presents a factory floor of interlocking stone, a puzzle of precision on a monumental scale, yet for a different kind of precision, one that only reveals itself from a god's eye view. We must look to the arid plains of southern Peru. Etched into the dark desert pavement of the Nazca region are hundreds of immense geoglyphs, lines and figures so vast they seem to belong to the landscape itself. Created by the Nazca culture between 500 years before the Common Era and 500 years after, these are not artifacts you can hold. They are artifacts you stand upon, or better yet, fly over. From the ground, they appear as shallow grooves in the earth, cleared of dark surface stones to reveal the lighter soil beneath. But from above, their true nature emerges, perfect geometric forms and elaborate animal figures spanning kilometers with breathtaking accuracy. A straight line runs for over 10 miles without deviating. A trapezoid stretches with parallel sides that remain perfectly aligned across impossible distances. A hummingbird, a spider, a monkey, each rendered with clean, continuous outlines that maintain perfect proportion despite their colossal size. This is where the mystery of ancient machining expands from the workshop to the horizon itself. The creation of these lines required a form of precision engineering applied to the very earth. Think of the challenge. The artisans could not see their work from above. They had to design and execute these perfect shapes while standing on the ground, with the curve of the planet and the rough terrain obscuring the overall form. To maintain such flawless straightness and alignment over kilometers implies the use of sophisticated surveying techniques far beyond simple stakes and ropes. Researchers like archaeoastronomers suggest the likely use of sighting instruments, perhaps a basic form of theodolite. This could involve a fixed central pole and a movable sighting rod, allowing teams to establish long, straight baselines by triangulation, creating a series of guide points across the desert. This is a method of transferring a small-scale blueprint to a gigantic canvas with minimal cumulative error. It is a systematic, almost machined approach to landscape alteration. The process itself would have demanded rigorous project management. Teams of workers following a master plan would clear the stones along predetermined paths, their work guided by those distant sighting markers. The consistency of the line widths, the sharpness of the corners where geometric shapes meet, all point to a repeatable, controlled process. It was not random artistry. It was a form of earthworks engineering governed by geometric principles and executed with assembly line discipline. The Nazca lines demonstrate that the drive for precision in the ancient world was not confined to objects. It could be scaled up to transform an entire valley into a precise, enduring diagram, a testament to a culture that thought in vast, measured lines and saw the land itself as a material to be shaped with exacting intent. A desert valley transformed into a perfect diagram speaks of a culture that measured the world in grand, straight lines. But sometimes the most puzzling artifact is not a line stretching for miles, but a small, dense mystery you can hold in the palm of your hand. In 1961, 3 rockhounds searching for geodes in the Coso Mountains of California cracked open what they thought was a promising stone nodule. Inside, instead of the expected crystal cavity, they found something utterly incongruous. Encased within the hardened clay and mineral layers was a cylindrical metal object with a porcelain-like insulator and a central rod, all held together by a rust-colored hexagonal collar. To anyone familiar with 20th century mechanics, it looked unmistakably like a modern spark plug. The story of the Coso artifact, as it came to be known, ignited a firestorm of speculation. Could this be definitive proof of advanced ancient technology, or even a visitor from another time, fossilized within a stone that supposedly took hundreds of thousands of years to form? The initial mystery was intoxicating. Here was an object of clear mechanical design, seemingly sealed inside a natural geological formation that predated human industry by eons. It appeared to be the ultimate out-of-place artifact, a literal spark of the modern world trapped in deep time. The allure of such a discovery is powerful, suggesting a hidden history where our timeline is not just incomplete but profoundly wrong. However, the true value of the Coso artifact lies not in what it ultimately was, but in the rigorous journey to understand it. As investigators and skeptics took a closer look, a more mundane, yet equally fascinating story emerged. The object was eventually identified by spark plug collectors as a 1920s-era Champion brand plug, a model used in early Ford Model T and Model A engines. The mysterious hexagonal casing was simply a corroded spark plug shield. The so-called geode was not a true geode with a hollow crystal center, but a hard concretion of clay and iron oxide that can form much more quickly around a metal object, especially in a moist environment. The lesson here is not one of disappointment, but of critical methodology. The Coso artifact forces a crucial question upon anyone searching for evidence of lost technology. How do we distinguish a genuinely anomalous object from a modern item that has been misinterpreted, either through natural processes or our own eager imaginations? This case study stands as a vital cautionary tale in our exploration. It reminds us that the path to understanding the past requires a delicate balance, a dual mindset of open-minded curiosity and relentless, grounded skepticism. We must be willing to chase the extraordinary possibility, but equally willing to follow the evidence wherever it leads, even if that leads back to a more ordinary explanation. In doing so, we sharpen our tools of discernment. We learn to ask better questions about context, material composition, and formation processes. The Coso artifact, now widely seen as a 20th century object in a natural concretion, did not close a door on mystery. Instead, it provided a masterclass in how to open the right ones, teaching us that the most important tool in archaeology is not a shovel, but a disciplined and questioning mind. The Coso artifact teaches us the discipline of separating modern echoes from ancient voices. But what about an artifact that is not a tool itself, but a key to using the world as one? Norse sagas speak of a mysterious object that allowed Viking navigators to conquer the treacherous North Atlantic, a realm where the sun could vanish for days behind cloud and mist. They called it the Solarstein, the Sunstone. While no definitive sunstone has ever been found in a Viking archaeological context, the persistent descriptions in their lore point not to a myth, but to a potential application of profound natural science. The leading candidate is a crystal known as Iceland spar, a transparent form of calcite. This is where the concept of advanced ancient machining expands into the realm of applied physics. Iceland spar possesses a unique optical property called birefringence. When light passes through it, the crystal splits the light into 2 separate rays. This creates a double image. For a sailor on a shrouded sea, this property could be life itself. By rotating a properly cut piece of this crystal and looking toward the sky, even through thick cloud cover, a skilled observer could detect a subtle change in the brightness of the dual images. The point where the two images matched in intensity would reveal the hidden azimuth of the sun, providing a fixed celestial reference point when the sky itself offered no visible clues. This transforms the crystal from a pretty mineral into a sophisticated optical instrument. But to function reliably, the sunstone could not be just any rough chunk of calcite. It would need to be carefully selected for clarity, then shaped with precision. The faces of the crystal likely needed to be cut and polished into specific planes to optimally exploit its birefringent qualities. This is a form of precision lapidary work, a machining of light itself. It demands an understanding of the crystal's internal structure and how to orient it correctly. The true sophistication, however, lies not just in the stone but in the system it enabled. The sunstone did not give a simple answer like a modern compass. It provided a single data point, the sun's direction. The navigator then had to integrate this information with their knowledge of the sun's path for that time of year, their dead reckoning of distance traveled, and their profound, almost intuitive reading of sea currents, bird flight, and wave patterns. This was a form of cognitive machinery, a mental algorithm for processing disparate environmental data into a reliable course. The hypothesized sunstone represents a fusion of three advanced domains: precise material preparation, a working knowledge of optical physics, and a complex, structured method of reasoning. It suggests that Viking mastery of the seas was not born from brute force or luck, but from a quiet, sophisticated technology of the mind and the hand, turning a clear crystal into a window through the clouds and a cornerstone of an empire built on waves. A clear crystal could guide a ship through fog, but the Byzantine Empire wielded a weapon that turned the sea itself into a blazing trap. Known to history as Greek fire, this was not a simple flaming arrow or pot of oil. It was a state secret of such immense power that its exact composition died with the empire that created it. Contemporary accounts from besieged sailors describe a horrifying spectacle, a viscous liquid that clung to everything it touched, burning fiercely even on water, defying all attempts to douse it with sand, vinegar, or waves. While the lost formula captivates chemists for our search, the true engineering marvel lies not in the fuel but in the projector. The Byzantines called it the siphon. This was not a simple tube. Historical texts and artistic depictions describe a complex apparatus, often mounted on the prows of their Droman warships. It was a system designed to eject a continuous, focused stream of this terrible liquid over a surprising distance, like a primitive, nautical flamethrower. The implications of such a device are profound. To project a liquid stream under force, especially a volatile, sticky, incendiary mixture, requires a carefully engineered system. Think of the components involved. First, a sealed reservoir to hold the unstable chemical mixture, likely made of thick bronze to resist corrosion and pressure. Then, a pumping mechanism, possibly a large bronze syringe operated by pistons or a robust bellows system, to create the necessary force. This pump would feed into reinforced bronze tubing, leading finally to a nozzle, a precisely shaped aperture that would focus the stream into a tight, controllable jet. The manufacturing precision needed here is significant. The bronze castings for the pump cylinders would need smooth, consistent interior walls to allow pistons to move without seizing. The valves controlling the flow would need to seat perfectly to prevent leaks or premature ignition. Every joint in the tubing and reservoir would need to be seamless, likely achieved through expert brazing or casting, to withstand both internal pressure and the corrosive nature of the fuel itself. This was not a one-off ceremonial object. It was a mass-produced weapons system deployed across the imperial fleet. Each siphon had to be reliable, durable, and interchangeable in its basic function. The creation of Greek fire projectors represents a chilling convergence of disciplines, advanced metallurgy to craft-resistant components, a grasp of fluid dynamics to design an effective delivery system, and precise mechanical engineering to assemble it all into a functional, terrifying whole. It stands as a stark reminder that the drive for precision in the ancient world was not always directed toward art or navigation. Sometimes it was forged in the dire necessity of conflict, yielding a weapon so advanced that its ghost, in the form of historical descriptions, still flickers with the heat of a lost and formidable technology. The terrifying precision of Greek fire projectors reveals an ancient world capable of engineering complex systems for a single, devastating purpose, but for a different kind of structural genius, one that speaks to patient, meticulous planning over centuries. We must look to the very bones of the world's oldest stone monuments. At sites like Sacsayhuamon in Peru and even the classical Parthenon in Greece, the true secret to their endurance is often hidden in the joints. Many of these colossal stone blocks were not simply stacked, they were locked together with metal clamps. This is not the mystery of the stones themselves, but of the perfect negative space created to hold the metal. The clamps, typically iron or bronze, were often poured into channels that had been carved directly into the hard granite or andesite. These channels are not rough gouges. They are precise geometric recesses, often shaped like a dovetail or an I-beam, designed to grip the molten metal as it cooled and solidified, creating an incredibly strong interlocking bond. The creation of these channels is where the engineering puzzle deepens. Imagine trying to carve a perfect dovetail slot with its angled sides deep into a block of granite using only a hammer and a chisel. The task is not just difficult, it demands a level of control that seems almost surgical. The walls of these recesses are clean and straight, the corners sharp. This level of precision in hard stone suggests something beyond simple pounding. It points to the likely use of specialized routing tools. One compelling theory involves a technique using a tubular drill, perhaps made of copper, but with a critical innovation. Instead of just sand, the drill might have been fed with an abrasive slurry and guided by a metal or wooden template fixed to the stone's surface. This template would act like a stencil, forcing the drill to follow the exact dovetail or I-beam pattern, effectively milling the shape into the stone through a process of guided abrasion. It is a form of subtractive manufacturing, removing material to create a perfect, repeatable form. But the sophistication does not end with the carving. The second act of this process reveals an equally advanced understanding of materials. Pouring molten metal, which is over 1,000 degrees Celsius, into a channel in cold stone is a risky operation. The drastic difference in temperature could easily cause the stone to crack from thermal shock. The fact that these clamps were successfully integrated tells us the builders possessed a nuanced knowledge of thermal expansion. They likely preheated the stone blocks, or perhaps used a stepped pouring process, introducing the metal in stages to allow for a more gradual transfer of heat. This indicates a multi-step manufacturing protocol, a carefully choreographed dance between stoneworker and metalsmith. Each clamp represents a fusion of disciplines, precise stone machining married to advanced metallurgical practice, all in the service of creating a structure meant to last for millennia. These hidden metal ligaments are a quiet testament to a forgotten school of structural engineering, one that thought in terms of permanent molecular bonds, locking mountains together not with mortar, but with forged geometric intention. The hidden metal ligaments locking stone together speak of a deep understanding of materials. But what if the material itself could be engineered to hold an edge of legendary sharpness? For over 1,000 years, the swords of Damascus were not just weapons, they were objects of awe. Their blades bore a mesmerizing, watery pattern, like ripples on a pond frozen in steel. More than their beauty, they were famed for a terrifying performance, able to slice through a silk scarf falling through the air and retain a keen edge through brutal combat. This was not a myth, but a lost technology called Wootz steel, originating in India as early as 300 years before the Common Era and traded to forging centers in the Middle East. True Damascus steel represents a pinnacle of ancient material science, a form of advanced machining at the atomic level. The secret was not in the hammer alone, but in a meticulously controlled recipe and process. It began with small, sealed clay crucibles. Inside, iron was combined with precise amounts of carbon-rich materials, like specific woods or leaves and sometimes trace elements. This crucible was then heated in a charcoal furnace to an exact temperature, melting the contents into a homogeneous ingot of high-carbon steel. This was the first act of control, creating a pure, uniform starting material. But the magic happened during the slow, careful cooling. As the ingot solidified over many hours, the carbon within it did not spread evenly. Instead, it formed into microscopic clusters of an incredibly hard compound called cementite. These clusters arranged themselves into bands and patterns within the softer steel matrix. The master smith then took this ingot and began the arduous process of forging, heating and folding it repeatedly. With each fold and hammer blow, those microscopic carbide bands were stretched, twisted, and redistributed, but never fully dissolved. They became the source of the iconic watery pattern, a visible map of the steel's inner crystalline world. This process demanded an almost intuitive yet repeatable understanding of variables modern metallurgists call carbon diffusion and crystal structure. The smith was not just shaping metal, he was orchestrating its internal architecture. He was manipulating the very arrangement of atoms through heat, time, and force, following a guarded formula that had been perfected through generations. The loss of this technique around the 18th century, as trade routes shifted and raw material sources changed, is a profound lesson. It shows that advanced ancient machining was not always about a lathe or a drill. Sometimes it was about a process, a repeatable sequence of chemical and thermal commands that transformed a lump of ore into a self-sharpening, resilient masterpiece. The Damascus blade is a reminder that the greatest tools are sometimes not the ones we see, but the invisible, inherited knowledge of how to make nature itself perform an impossible feat. A blade could be honed to perfection through controlled chemistry, but could an instrument be crafted to sense the very heartbeat of the planet itself? In the year 132 of the Common Era, during China's Han Dynasty, the brilliant polymath Zhang presented the emperor with a creation that seemed to border on prophecy. He called it the Hufeng Didongyi, an instrument for inquiring into the wind and the shaking of the earth. This was the world's first known seismoscope. Historical records describe an ornate bronze vessel, perhaps over 6 feet wide, adorned with 8 dragons facing the cardinal and intercardinal directions. Below each dragon's open mouth sat a bronze frog, head tilted upward, ready to receive. Inside this vessel, the genius was hidden. While the exact internal mechanism is lost, the most accepted theory involves a carefully balanced inverted pendulum. Think of a heavy mass delicately suspended from the top, free to swing in any direction. At the faintest tremor from a distant earthquake, the pendulum would sway, its motion amplified by the vessel's shape. This movement would trigger a sophisticated release mechanism, likely a set of levers or catches, causing one specific dragon to open its jaw and release a bronze ball with a loud clang into the mouth of the waiting frog below. The direction of the earthquake was indicated by which dragon released its ball. The reported accuracy of this device, said to have detected a quake hundreds of miles away that no one at the capital had felt, is what transforms it from a curious artifact into a milestone of precision engineering. Consider the sensitivity required. The pendulum had to be balanced with exquisite care, suspended in a way that friction was minimized so the faintest vibration from far below the earth could set it in motion. The release catches holding each dragon's ball had to be finely tuned, tight enough to hold the weight securely against normal disturbances, yet instantly responsive to the precise minute push of the swinging pendulum. This is a machine built to detect the invisible. It demanded not just an understanding of mechanics, but a philosophy of measurement. Each component, from the bronze castings of the dragons to the internal levers, had to be manufactured to consistent, exacting standards. The dragons' mouths, the tracks for the balls, the pivot points of the pendulum, all required tight tolerances to function as a unified system. A slight imperfection in the casting, a bit of excess bronze in a hinge, and the entire delicate trigger system would fail. Zhang Heng's seismoscope was not a tool of force but of amplification. It took an imperceptible signal and translated it into an unambiguous physical event. Its existence speaks of a workshop culture that had mastered the art of calibration, where artisans and engineers collaborated to build instruments that extended human perception beyond the limits of the senses. It stands as a quiet argument that the ancient drive for precision was not always about shaping stone or forging steel. Sometimes it was about listening with a machine's perfect ear to the deep and distant rumble of the world itself. The quiet listening of a seismoscope gives way to a landscape of silent, unanswered questions. In the mist-shrouded highlands of northern Laos, the Xiankong Plateau holds a mystery carved in stone on a staggering scale. Here, scattered across dozens of sites, lie thousands of massive stone jars. They are not delicate vases, but colossal containers carved from solid sandstone and granite, some standing over 3 meters tall and weighing several tons. Their origins are lost to time, attributed to an Iron Age culture that left no written records, and their purpose remains one of archaeology's great enigmas, with theories ranging from burial urns to giant fermentation vessels for rice wine. Yet beyond their mysterious function, their very form presents a quieter, more technical puzzle. Look at the jars themselves. Many exhibit a remarkable cylindrical symmetry. Their bodies curve inward and outward in smooth, consistent arcs, and their rims are often perfectly level, as if designed to hold a lid. This is not the haphazard shape of a stone pounded into a hollow. This is the controlled form of a cylinder. On such a massive scale, achieving this consistency is a profound challenge. A single artisan with a hammerstone could certainly hollow out a rock, but to give that hollow a uniform, circular cross-section from top to bottom is a different matter entirely. The likely method points to a simple but brilliant application of mechanical principle. Imagine a central axis point established at the top and bottom of the raw stone block. By stretching a cord or fixing a guide along this central line, workers could have a constant reference for the jar's intended radius as they worked. As they pecked and ground away the stone, they could continually check their progress against this guide, ensuring they did not dig too deep or leave a bulge. This transforms the process from random sculpting into a form of manual machining. The tool, whether a hammerstone or a chisel, is guided by a fixed geometric rule. It is a primitive but profoundly effective lathe-like operation, where the stone remains stationary and the concept of rotation is implied by the symmetry of the final product. The sheer quantity of these jars, thousands of them across the plateau, reinforces this idea of systematic production. This was not a one-off ceremonial effort. It was an industry. The makers had a standardized shape in mind, and they developed a repeatable technique to achieve it. A technique that leveraged the basic principle of rotating a form around a central axis, even if the stone itself never moved. The plane of jars demonstrates with quiet power that the drive for precision and repeatability is not always about microscopic gears or flawless flatness. Sometimes it is about imposing a simple, perfect geometric idea upon the landscape itself, one colossal, symmetrical jar at a time, leaving behind a field of silent vessels that hold not relics, but the enduring echo of a methodical, scaling mind. A landscape of colossal jars demonstrates a culture thinking in massive, symmetrical forms. Yet for a mystery of a far more intricate and personal scale, we must shrink our gaze to an object that fits comfortably in the hand. Scattered across the former territories of the Roman Empire, from Britain to Hungary, are curious bronze artifacts that defy easy explanation. They are the Roman dodecahedra, small, hollow objects, each one a perfect geometric solid with 12 flat pentagonal faces. Every face contains a circular hole of varying size, and at each of the 20 corners sits a small knob. Over 100 of these enigmatic items have been found, and not a single contemporary text or image explains what they were for. This very absence of purpose is what makes them so compelling to our search. They are not tools of war, nor pieces of jewelry, nor obvious religious icons. They are pure, manufactured mystery. The guesses from modern researchers are a fascinating list of possibilities, ranging from practical candlestick holders to esoteric dice for games of chance, from knitting gauges for crafting gloves to sophisticated surveying instruments for calculating distances. Yet while their function remains locked in silence, their form speaks volumes about the technical capabilities of their makers. The machining mystery here is not about moving mountains of stone, but about achieving perfect, repeatable complexity in metal. Look at the object itself. Each dodecahedron is a model of geometric consistency. The 12 pentagons are identical in size and shape. The holes, though differing in diameter from face to face, are perfectly circular and consistently placed. This is not the work of a metalsmith free-handing a design. This is precision work. How was it done? One strong possibility involves the lost wax casting method, a technique the Romans mastered. To create such an object, a craftsman would first sculpt a perfect model of the dodecahedron in wax, ensuring each face and hole was exact. This wax model would then be encased in clay to create a mold, the wax melted out and molten bronze poured in. The challenge here is in that initial wax model. Creating a perfectly symmetrical, multi-faced solid by hand is incredibly difficult. It strongly suggests the use of a template or a guiding tool, perhaps a form of geometric compass or a cutting jig, to ensure every pentagonal face was identical before the casting process even began. This is a tool to make a tool. Alternatively, some dodecahedra show signs of being fabricated from sheet bronze. In this method, 12 separate pentagonal panels would need to be cut out with absolute precision, their edges folded, and then soldered together along perfect seams. This demands not just careful measurement, but also a high degree of skill in metal joining to create a hollow, airtight object. Whichever method was used, the result is the same, a standardized product. The dodecahedra found across vast distances share the same fundamental design and proportions. This uniformity is the key point. It tells us these were not unique artistic experiments. They were made to a pattern, implying a workshop tradition, a set of instructions, and a manufacturing process that could be replicated from one province to another. They were, in essence, mass-produced puzzles. Their ultimate use may be lost, but their very existence is a clear signal. They are proof of a Roman industrial mindset that could conceive of, and reliably produce, objects of perfect geometric complexity for a purpose so commonplace to them that they never thought to write it down, leaving us only the polished, enigmatic bronze form to ponder. The Roman dodecahedra remind us that standardization could be a mystery in itself, but one Roman system was built on a principle of flawless, functional clarity. To truly appreciate the scope of ancient machining, we must sometimes look not at a single artifact, but at an entire civilization's circulatory system. The sprawling aqueducts, public baths, and private plumbing of the Roman Empire were not just feats of grand architecture, they were triumphs of precision manufacturing on an industrial scale. This network, which brought fresh water to cities and carried waste away, functioned because of thousands of identical, meticulously made components. Think of the humble lead pipe. Romans did not just pour molten lead into rough trenches. They manufactured pipes. Skilled workers would cast lead into large, thin sheets. These sheets were then carefully rolled into cylinders, with the edges meeting in a straight seam. That seam was not simply folded over. It was meticulously soldered with a lead-tin alloy to create a perfect, watertight seal. The true engineering marvel lies in the consistency. Pipes of specific diameters were needed for different water pressures and volumes throughout the system. To achieve this, the rolling process likely used simple forms or mandrels, basic tools that ensured every pipe of a given class had the exact same internal diameter. This is the essence of standardization, creating interchangeable parts for a vast, complex machine made of stone and water. But the sophistication went far beyond the pipes themselves. Inside the homes of the wealthy and within the public bathhouses, water was not just flowing, it was being controlled. Bronze faucets, stopcocks, and valves were common. A simple Roman valve was a masterpiece of small-scale machining. It consisted of a bronze casing with an internal chamber and a rotating plug, often made of wood or bronze, that could be turned to block or allow the flow of water. For this to work without constant leaking, the fit between the rotating plug and its housing had to be exceptionally precise. The surfaces where metal met metal needed to be smooth and closely matched. Furthermore, many of these fixtures utilized threaded parts. The concept of the screw thread, allowing for adjustable, secure fastening, was well understood and implemented. Creating consistent, functional threads on bronze fittings required specialized tools, perhaps simple dies or taps, that could cut the helical groove into a rod or inside a hole with repeatable accuracy. This is not blacksmithing, this is precision machining for hydraulic control. The entire Roman water system, therefore, presents a different kind of artifact, a distributed one. It was a living network that depended on the mass production of watertight seals, uniform diameters, and reliably functioning valves. A single poorly soldered pipe or a badly threaded valve in a critical location could undermine the entire effort. The system's success proves that Roman workshops had moved beyond crafting unique items. They had embraced the logic of the production line, where the goal was to make hundreds or thousands of a single part that performed its one job perfectly, so that the greater system, the lifeblood of the city itself, could pulse without fail. This was not art for contemplation, but engineering for survival and comfort, built on a foundation of quiet, unyielding precision in lead and bronze. The logic of the Roman production line gave cities the gift of flowing water, but on the most isolated inhabited island on Earth, another civilization performed an engineering marvel for a different purpose entirely. Easter Island, or Rapa Nui, is synonymous with the silent, imposing moe, those monolithic stone figures gazing inland. Yet the common image of them as mere heads is a modern illusion, born from seeing statues buried up to their necks. Excavations reveal most have full torsos, some standing over 10 meters tall, but the true pinnacle of their construction is often overlooked, the massive cylindrical top-knots that crowned many of these giants, known as pucao. Carved from a distinctive red volcanic rock called scoria, these pucao could weigh over 10 tons each. Placing such a colossal stone cylinder on top of a statue's head, often at a significant height, is a staggering feat of leverage and coordination that continues to inspire debate. Yet the machining question here is more subtle, lying not in the placement but in the preparation. The pucao itself is a roughly cylindrical form, shaped from a much larger, irregular block of porous scoria. Shaping this lighter but still formidable stone into a consistent cylinder, especially one of such scale, implies a methodical process. It likely involved establishing a central axis and systematically removing material around it, perhaps using guidelines or a simple rotating platform to check for symmetry. a massive, slow-motion version of turning a spindle on a lathe. But the true precision lies in the joinery. The bottom of the pukao was not simply set flat on the head. Many show evidence of being carved with a concave mortise, a hollowed-out socket, designed to fit onto a corresponding convex tenon or knob carved on the crown of the moai's head. This is large-scale stone joinery. For this connection to be stable, resisting the island's fierce winds, the two carved surfaces had to complement each other with remarkable accuracy. The concave curve inside the pukao needed to match the convex curve of the statue's head with enough closeness to distribute the enormous weight safely. Achieving this required careful measurement and transfer of dimensions from the completed statue to the pukao still being shaped in a separate quarry. It suggests the use of templates or measuring cords to capture the profile of the tenon, so the reciprocal shape could be carved into the top knot. This is a process of intentional, precise fitting. It transforms the act from one of brute force lifting to one of calculated assembly, where two giant stone parts made in different locations are engineered to lock together in a stable union. The pukao are not merely decorative symbols, they are the final, crowning testament to a culture that mastered its landscape with a sophisticated understanding of form, balance, and the quiet, precise art of making stone embrace stone. A stone cylinder locked perfectly atop a giant statue speaks of controlled, deliberate assembly, but across the wind-swept hilltops of Scotland and parts of continental Europe, a different kind of stone transformation whispers of something far more volatile. Here, the ruins of ancient forts hold a startling secret. Sections of their massive stone walls are not merely collapsed, but fused together into a strange, glassy substance. This is vitrification. The very rock itself has been melted and resolidified, turning into a crude, dark glass. To achieve this, the stone had to be subjected to a sustained, searing heat exceeding 1,100 degrees Celsius. That temperature is not just hot, it is a furnace heat, far beyond what an ordinary wood fire or even a large bonfire could produce. This presents a double mystery, both how it was done and, more perplexingly, why. The why is a puzzle that divides researchers. Was it intentional, a form of ancient architectural engineering? Some argue that vitrifying the stone could have strengthened the wall, welding the loose rubble together into a single, monolithic, and more defensive barrier. Others suggest it could have been a catastrophic accident, the result of a devastating siege fire that grew so uncontrollably hot it literally melted the fortifications it was meant to breach. Yet even the accident theory raises profound questions about scale and fuel. To generate that kind of heat across large sections of a wall would require a tremendous, concentrated fuel source and likely some method of intensifying the combustion, like cleverly designed airflow channels or the use of specific, resin-rich woods and materials. It would have been a firestorm of almost industrial ferocity. This leads us to the how and the concept of thermal machining. Whether by design or disaster, the process represents a controlled, or at least channeled, application of extreme temperature to permanently alter the structure of stone. It is a form of pyrotechnology that borders on industrial processing. To melt rock on this scale is not about an open flame, it is about creating a sustained, localized oven. Imagine stacking the right fuels against the wall in a specific configuration, perhaps with clay or earth baffles to direct and contain the heat, turning the wall itself into the lining of a temporary blast furnace. The builders or attackers would have needed a sophisticated understanding of thermodynamics in practice, manipulating fuel, oxygen, and insulation to push a localized environment to a temperature that should have been beyond their reach. The vitrified forts stand as scorched monuments to a forgotten mastery of fire, not as a tool for warmth or cooking, but as a geological force capable of reshaping the landscape itself. They challenge us to see these hilltops not just as defensive positions, but as the sites of ancient experiments in material transformation, where stone was not just stacked but remade. The silent, glassy scars of vitrified forts reveal an ancient power to melt stone itself. Yet a different kind of permanence was being forged in the workshops of ancient India, not through fire's destruction, but through metal's defiance. While the rust-resistant pillar in Delhi stands as a famous marvel, it is not alone. Across the subcontinent, other iron monuments whisper of a sustained, sophisticated tradition. The Dihar iron pillar, for instance, shares that same stubborn refusal to corrode, a testament to a metallurgical knowledge that was not a lucky accident, but a repeatable craft. These artifacts speak to a culture that had mastered iron on a monumental scale, producing metal of astonishing purity and durability. But the true engineering feat goes beyond the chemistry of the alloy. It lies in the physical challenge of shaping these colossal metal masses. Think of the process. To create a pillar over 20 feet tall and weighing several tons, blacksmiths first had to produce the iron itself in a large, efficient furnace. Then came the forging. This was not about crafting a sword or a plow. This was industrial-scale metalworking. The glowing iron, white-hot and plastic, had to be manipulated by teams of workers using immense tools. They likely employed massive trip hammers, heavy weights lifted by ropes or levers, and then dropped onto the metal, perhaps powered by water wheels or animal labor. This is a crucial step toward mechanization. It represents the integration of an external power source with a specialized tool, amplifying human strength to a degree necessary for the task. The hammers themselves would have been massive blocks of iron, and the anvils upon which the pillar was worked would have been monolithic stone or metal blocks, sunk deep into the earth to absorb the tremendous force. Every strike had to be coordinated. Every weld between the countless smaller iron pieces had to be flawless, as a single slag inclusion or cold seam could create a hidden weakness. The resulting pillars are not just objects, they are records of a forgotten industrial process. They required advanced smelting for the pure metal, advanced mechanics for the shaping tools, and advanced logistics to coordinate the labor. This was a form of machining through coordinated, amplified force, dedicated to a single, profound goal: to create something from iron that would stand, unyielding and untarnished, as a permanent marker of human achievement against the relentless decay of time. The colossal iron pillars of India stand as a testament to a culture that mastered metal on an industrial scale. Yet another civilization, centuries earlier and half a world away, achieved a similar mastery over stone, not through fire or force, but through a system of absolute, repetitive precision. In the ancient city of Hebron, the massive enclosure built by Herod the Great around the Cave of the Patriarchs presents a different kind of marvel. Its walls are composed of thousands of enormous limestone blocks, each one a lesson in controlled geometry. This is Herodian masonry, a style so distinctive it acts as a signature across the king's building projects. At first glance, the blocks appear simple, but a closer look reveals the secret. Each face is perfectly flat, a smooth plane that meets its neighbor with a hairline seam. But the true hallmark is the drafted margin, a raised, meticulously crafted border that frames the central, slightly recessed panel of the stone. This is not decorative carving. This is evidence of a manufacturing protocol, creating such a feature by hand with a hammer and chisel, on block after block, and maintaining perfect consistency across an entire wall, would be an exercise in superhuman patience and skill. The uniformity is simply too perfect. It suggests the use of a physical guide, a jig or template that transformed a complex task into a repeatable process. Imagine a wooden or metal frame fixed to the stone's surface. This frame would have a precise opening, establishing the exact width and depth of the recessed panel. The mason, using a pointed chisel or a pick, would then work only within that open area, knowing the frame itself protected the raised border from any stray strikes. It was a form of stencil for stone. This simple apparatus, a primitive but brilliant machining jig, allowed teams of workers, perhaps with varying levels of skill, to produce identical results. Every block that emerged from this process was a perfect component, designed to interlock seamlessly with its neighbors, creating a wall of such imposing, flawless regularity that it projected an aura of unshakable power and eternal order. The system turned the chaotic act of stone dressing into a calm, mechanical operation. It demonstrates that the ancient pursuit of precision was not always about a single, miraculous artifact. Sometimes it was about the quiet genius of the production line, about inventing a method to impose perfect order, one identical, drafted stone at a time, until an entire fortress of geometry rose from the earth. Herod's drafted margins turned stone into a system of interchangeable parts, a language of perfect geometry. Yet another artifact from the ancient world speaks in a different kind of language entirely, one whose meaning remains locked behind a door of pure mechanical precision. In the ruins of the Minoan palace of Phaistos on the island of Crete, archaeologists uncovered a small, fired clay disc, roughly the size of a modern dinner plate. Dating to the second millennium before the Common Era, the Phaistos disc is not remarkable for its size or material. Its power lies entirely on its surface. Both sides are covered from the outer edge spiraling inward with a sequence of tiny, intricate symbols. There are human figures, birds, plants, shields, and abstract marks, all arranged in clear, deliberate groups. For over a century, scholars have attempted to decipher this script, debating whether it represents a hymn, a law, or a story. But while the message remains a tantalizing secret, the method of its creation is a clear and undeniable statement of technical capability. Each symbol on the disc was not drawn or carved by hand. It was stamped, impressed into the soft clay with individual, reusable seals before the disc was baked hard. This single fact transforms the object from a written document into a manufactured product, and its true mystery shifts from linguistics to mechanical engineering. To create the disc, a Minoan artisan first had to create the stamps. This required a set of precisely carved dies, each one a mirror image of the intended symbol. Think of the process in reverse: the fine lines of a running man, the delicate feathers of a bird, the clean curves of a lily, all had to be carved in perfect, raised relief on the end of a small seal, likely made of wood, bone, or metal. When this seal was pressed into clay, it would leave its positive, recessed image behind. Carving these dies is where the concept of advanced machining enters the picture. The symbols are small, some only a few millimeters across. To carve such intricate, raised details on a hard material demands tools of exceptional sharpness and stability. This was likely the work of a master toolmaker using hardened metal gravers, fine chisels with needle-like points. The artisan would have worked under magnification, perhaps with a simple lens or by relying on extraordinary eyesight and a steady hand, removing minute slivers of material to define each line and curve. The stamp for a single symbol was a miniature sculpture in negative, a master template designed to be used again and again. This makes the Phaistos disc evidence of a two-stage manufacturing process. First, the precision machining of the tool, the stamping die. Second, the use of that tool to produce a reproducible text. It is, in essence, an early and sophisticated form of movable type, a technology that would not become widespread for another 3,000 years. The disc itself is not the marvel of machining, the stamps are. They represent a workshop where the goal was not to make one beautiful object, but to create a perfect, durable tool that could generate countless identical impressions. This speaks to a mindset focused on replication and standardization, on the very idea of communication as something that could be mechanized. The Phaistos disc, therefore, holds a dual mystery. We yearn to know what its spiraling symbols say, the story they tell of a lost Minoan moment, but perhaps the louder message is in their flawless, repeated form. They tell us that in a palace on ancient Crete, someone had already mastered the quiet, precise art of building a machine to speak. These 25 artifacts are not isolated curiosities. They form a scattered constellation, each one a point of light illuminating a hidden pattern across the dark canvas of the past. From the geared astronomy of the Antikythera mechanism to the molecular purity of an Ulfberht blade, from the machined flatness of an Egyptian sarcophagus to the earth-scaled geometry of the Nazca lines, they collectively whisper a single, persistent question. What if our understanding of progress is incomplete? These objects do not demand we believe in ancient astronauts or sunken super-civilizations. Instead, they ask for a more nuanced view. They suggest that human ingenuity has flared in brilliant, localized intensities, that pockets of advanced technical insight have been achieved, mastered, and then, for reasons of catastrophe, secrecy, or simply the fragility of knowledge, have faded from the common record. History, as written, often feels like a smooth, upward slope, but these artifacts present it as something richer and more mysterious, a complex tapestry. Woven into its fabric are threads of profound knowledge that snapped, threads we are only now, with our modern tools and perspectives, beginning to trace again. This is not about replacing one dogma with another. It is about embracing a more humble and curious stance toward our ancestors, the disciplined study of these objects, separating genuine enigmas from modern misunderstandings, as with the Coso artifact, is where true discovery lies. It requires both wonder and rigorous skepticism, a willingness to be amazed by the precision of a Roman dodecahedron, while also demanding clear evidence for its origins. This journey across continents and millennia leaves us not with definitive answers, but with a far more valuable gift: better questions. It expands our sense of the possible. What other chapters of technical achievement lie buried, not in conspiracy, but in the simple gaps of our archaeological record? What forgotten principles of construction, chemistry, or mechanics might still be latent in these silent stone and metal forms, waiting for a new generation to recognize them? The story of human innovation is far from fully told. If this exploration into the edges of history has sparked your curiosity, there are countless more puzzles waiting. Consider subscribing for deeper dives into the world's greatest historical mysteries, and we would love to hear your perspective. Which of these artifacts do you find most compelling, and what other enigmatic objects do you think belong in this conversation? Share your thoughts in the comments below. The search for understanding is a conversation that spans generations, and your voice is a part of it. Thank you for joining this exploration.